When Vladimir Putin introduced the 3M-22 Zircon missile, known by its NATO code SSN-33 in recent years, it was accompanied by digital animations that left Western analysts. The presentations promised technology straight out of science fiction, a weapon flying at 9 times the speed of sound, capable of sending American aircraft carriers to the bottom with a single strike, ignoring any air defenses, and completely changing the rules of 21st century naval warfare. But unfortunately for the Russians, after its introduction into service in 2023 and subsequent deployment in the war in Ukraine during 2024, Western and Ukrainian experts now have enough hard data to work with. It's time to strip this military chimera of layers of Kremlin propaganda and take a look at the cold technical reality. After all, unlike Russian generals, the laws of physics are not corrupted by any political agenda. The laws of physics don't take bribes. First, let's look at the history of development, at its roots in the darkness of the Cold War. Zircon didn't just appear overnight from the genius of today's Russian engineers. Its pedigree goes deep into the Soviet era, specifically into the 70s and 80s of the 20th century. The Soviet Union was well aware at the time that it couldn't compete with the American Navy in terms of conventional surface fleets. American carrier groups were protected by an impenetrable umbrella formed by Aegis systems and F-14 Tomcat fighters. The Soviet asymmetric response was supposed to be missiles, fast, heavy, and launched in large numbers. The predecessor of hypersonic ambitions was a research program from the late 70s and early 80s, carried out by the MPO Mashinostroyenie Design Bureau in Roitov, which is the same bureau behind the Zircon as well. At that time, the Soviets were experimenting with experimental devices like Gala, which was a hypersonic aircraft developed based on the H-90 missile. And later, in the 90s, they continued with the Zberoslavensky project Kolod, which was basically a flying laboratory testing the first generation of Scramjet engines running on liquid hydrogen. However, after the collapse of the Soviet Union, the ambitious program almost came to a halt due to a total lack of funding. The paradox of history is that in the 90s, on the Kolod project, NASA cooperated with the Russians both financially and scientifically, wanting to understand the dynamics of scramjet engines. After that, there were several years of calm, but then a secret restart came in the new millennium. With the rise of Vladimir Putin to power and the increase in oil prices, military coffers were filled again. And around 2011, the project was officially designated under the codename 3M-22 Zircon. The task was clear: to create a missile that would fit into the existing vertical launch silos from which Russia launched subsonic Kalibr missiles and supersonic Onyx missiles. This would eliminate the need to build entirely new ships for the new superweapon. And what happened next? Then followed a decade of testing and political fanfare. The first ground tests of maquette began around 2012 or 2013. But the breakthrough came in 2016 and 2017 when Russia conducted a successful first flight test from ground ranges. At that time, state news agencies proudly announced for the first time that the missile had reached Mach 8. In March 2018, Zircon then became one of 6 superweapons, which Putin personally presented in his famous speech to the Federal Assembly, where he showed animations of attacks on the United States. Since 2020, testing has moved to the sea. The main testing platform became the new frigate Admiral Gorshkov. In October 2021, the Zircon was successfully launched for the first time from a submerged Yasen-class nuclear submarine, Severodvinsk. And in January 2023, Putin, with great fanfare, sent the frigate Admiral Gorshkov with Zircons on board on a long voyage across the Atlantic and Indian Oceans, which was meant to demonstrate the global reach of Russian hypersonic power. However, a year later, reality struck. Or rather, with Ukrainian air defense. But before we head into the war in Ukraine, we need to find out how Zircon is actually supposed to work. To be fair, technologically, it's a very impressive weapon. It's not a scam or a cheap trick. In aviation, it's necessary to strictly distinguish between two types of hypersonic weapons. Maybe three, but we don't consider ballistic missiles to be hypersonic weapons, so we won't bring that up here. Anyway, the first type is aeroballistic missiles like the KH-47M2 Kinjal, which is basically just a modified Iskander ballistic missile adapted for launch from a MiG-31K fighter jet. The Kinjal does fly at hypersonic speeds, but it's powered by a conventional solid-fuel rocket engine. It reaches its speed right at the beginning and then flies the rest of the trajectory by inertia, gradually slowing down due to the drag in the dense air. But Zircon is a whole different league. It's a true cruise missile, meaning a hypersonic cruise missile. It doesn't perform any passive ballistic fall from space along a predictable curve like the Oreshnik or, for that matter, any intercontinental ballistic missile. No, Zircon stays in the Earth's atmosphere the entire time. It flies basically horizontally, and during the entire middle phase of the flight, it is actively powered by its engine. Under ideal conditions and with perfect connectivity, this would allow it to change direction and altitude, making it impossible for defenders to calculate the impact point in advance. The secret of this technology lies in an extremely complicated two-stage propulsion system. It consists of a combination of two engines, a scramjet and a rocket engine. The scramjet engine has one fundamental mechanical disadvantage. It cannot start from a standstill, that is, from zero speed. In order to even start, it needs air to flow into it at enormous pressure. That's why Zircon first has to use brute force. After a vertical launch from the Universal 3 S-14 cells, which are carried by Russian frigates and submarines, a massive solid fuel launch booster ignites. This rocket stage acts as a kind of slingshot. Within just a few seconds, it generates enormous thrust. It hurls the missile to an operational altitude between 30 and 40 kilometers, where the air is already thin enough not to produce fatal drag, but still contains enough oxygen for combustion. And at that moment, the rocket engine gives the missile a speed exceeding Mach 3.5 to Mach 4. At this moment, the launch booster fulfills its role. It burns out and is jettisoned. At the moment the booster is jettisoned, the intake of the main engine is exposed and the technological marvel known as the Scramjet or supersonic ramjet engine is ignited. You can imagine it as a kind of shaped hollow tube. Unlike the engines in regular transport or fighter aircraft, you won't find a single moving part in it. No shafts, no rotating blades in the compressor, no turbine. The compression of air, which is necessary for efficient combustion, is ensured purely by the geometric shape of the intake opening and the insane forward speed of the missile itself. Air is literally forced into the engine by enormous ram pressure, and the operation of the scramjet is divided into 3 microsecond steps. It starts with supersonic compression. In a classic ramjet engine or ramjet, the airflow inside the engine slows down below the speed of sound. In a scramjet, where the SE stands for supersonic combustion, the air rushes through the entire inside of the engine at supersonic speed the whole time. Then comes the next microsecond part of the engine's operation. Because into this supersonic blast rushing through the combustion chamber, nozzles start injecting a special synthetic fuel under enormous pressure, which is called Desilin M in Russia. The mixture has to blend and ignite within milliseconds. That's why, in aerodynamics, this situation is often compared to trying to light a match in a hurricane. If the flame goes out or moves in the wrong direction, the engine will immediately lose thrust and the missile will crash. However, once the fuel ignites, the explosive combustion creates enormous pressure. The exhaust shoots out through the narrow nozzle at the end of the missile, which generates constant forward thrust. This process keeps the Zircon in the hypersonic regime, that is, at speeds above Mach 5 for thousands of kilometers until the fuel runs out. All of this happens within milliseconds during the operation of a scramjet engine and requires absolute mastery of materials. During a long flight at speeds above Mach 5, air friction causes the surface of the missile to heat up to temperatures exceeding 1,500 to 2,000 degrees Celsius. Ordinary aviation alloys would either melt like wax in such intense heat or lose their structural strength because, of course, when you have a metal, it may only start to melt at a certain temperature, but it loses most of its strength and structural integrity at much lower temperatures than its melting point. In any case, if such high temperatures occurred with ordinary alloys, the missile would fall apart. The air pressure would shatter it. That's why the Russians had to develop special heat-resistant materials for the Zircon missile, combining carbon composites, and advanced ceramics that can insulate the missile's internal structure and the engine itself from this heat. It is precisely in this material chemistry and the aerodynamics of the combustion chamber where the greatest technological achievement of the entire 3M22 project lies, and this is truly a Russian masterpiece. This is what has come closest to being a real functioning hypersonic missile. But as we said, not everything in the laboratory is the same as in combat conditions, and its baptism of fire came in Ukraine. And with it came the end of the myth about the invincibility of the Zircon missile. Because the Zircon missile looked terrifying on paper and in Russian Ministry of Defense animations. A speed of around Mach 9 and a range of over 1,000 kilometers were supposed to shorten the defender's early reaction time to just tens of minutes. The kinetic energy of the impact alone from such a fast object would literally tear a modern warship to pieces, even without an explosive warhead. Let me remind you that the Zircon missile was originally intended to be loaded onto frigates and used as an anti-ship missile, primarily against aircraft carriers. However, in February and March of 2024, the situation changed radically. Russia used Zircons in combat for the first time during a combined attack on Kyiv. Although the missile was originally developed for naval combat against aircraft carrier groups. Ukrainian experts from the Kyiv Research Institute of Forensic Expertise managed to secure relatively intact debris from the downed missiles, thoroughly analyze their components, and confirm the identity of the weapon. And what was the result? Ukrainian air defense showed that the Kremlin's tales about an unstoppable weapon were highly exaggerated. Western anti-missile systems, specifically the Patriot PAC-3 with MSE kinetic interceptors and the European SAMP-T system, were able to successfully detect, target, and also destroy the Zircons. Not even Russian propaganda could fool physics and design limitations. And that's for two fundamental reasons. The first problem is the phase of fatal deceleration, which occurs with Zircon. In order for Zircon to be able to lock onto the target and perform a guidance maneuver in the final phase of flight, that is, during the descent to the target, it has to significantly slow down in the denser layers of the atmosphere. Data from Ukrainian radars showed that during descent, Zircon's speed drops to around Mach 4.5. At that moment, the hypersonic Phantom becomes just a very fast supersonic cruise missile. The Patriot PAC-3 system was designed to intercept such missiles back in the 1990s. At that moment, even Zircon isn't a hypersonic missile anymore, because it's not flying faster than Mach 5. And that brings us to another critical problem, which is the plasma shield that acts both as a beacon and as a cover at the same time. At speeds above Mach 5, the air in front of the object is compressed and friction becomes so intense that the gas ionizes, creating a layer of hot plasma around the missile. Russian media claimed that this plasma acts as an invisible cloak because it absorbs radio waves. But the joke is that the plasma reliably blocks the missile's own radio sensor, so at that stage of flight it basically flies blind and, apart from inertial guidance, can't correct its course. And of course that causes inaccuracies. However, at the same time, this plasma creates a bright beacon on the defender's radars, impossible to miss both thermally and electromagnetically. As soon as the plasma trail enters the coverage zone of modern radars like the AN/MPQ-65, the system immediately calculates the interception point. This is a big simplification of the plasma effect, and we'll get into it in more detail later. However, besides these two problems that occur in practical use, there's also a third problem, and that's the problem with every superweapon. Namely, that it's very expensive and it's handmade. The analysis of the wreckage revealed that while Zircon is not a hoax, technologically it's an exceptionally advanced weapon whose construction and metallurgy can only be handled by a handful of countries in the world. However, the Russian military-industrial complex is running into the classic Soviet syndrome. It can't bring advanced technology from lab prototypes into efficient mass industrial production. To produce a single Zircon, you need advanced alloys and a Scramjet engine. You need Western microelectronics, which are necessary to produce these things. And of course, all of this makes it terribly expensive. One missile costs around $10 million. And that means Russia is able to produce at most a few dozen units per year. The production of a single Zircon is essentially like precision watchmaking, with a huge amount of manual labor. In the wreckage of the missiles, components from Western consumer electronics were also found, which Russia has to smuggle through third countries to circumvent sanctions. According to leaked reports from the NPO Mashinostroyenie arms sector, Russia is able to produce these missiles only tens of them per year, not hundreds. In a high-intensity war of attrition, where ammunition is consumed by the thousands, the Zircon thus remains more of an exclusive political tool for special terror attacks on cities or very precise strikes, rather than a weapon with real military potential to change the course of the war on the front line. The Zircon has undoubtedly forced Western strategy to evolve its naval tactics. Modern air defense has to react to it instantly because the window to intercept the target is extremely narrow. However, there is no technological revolution that would wipe Western armies off the map with a single stroke. The Ukrainian battlefield has once again shown an old familiar truth. There is often a huge difference between how a weapon looks in a flashy PowerPoint presentation meant for the eyes of dictators, and how it actually performs against modern Western technology in the dust and chaos of a real battlefield. These are things that are often very different from each other, but let's get back to that plasma problem. Let's talk in detail about how it actually works, why it acts as a shield for some radars, and at the same time as a beacon for other radars. About how that plasma problem works, which messes things up for the Russians and at least gives the Ukrainians a chance to shoot it down. We'll talk about that in the bonus section on our hero page for supporters or podcast members. You can already find it there. I hope you like this old new format of videos because it's coming back. It's actually a podcast format where the images mostly serve just as a supplement and it's mainly about listening, but at least there are some images and it's a bit more narratively refined than those videos that come from streams and react purely to current events. Of course, the more edited, faster, and more cut videos that you're used to from the past will probably return as well. In any case, let me know how you like the podcast, Support the content through QR codes with a like, sharing, or spreading the word, and I'll see you again. Next time, check out the bonus on Hero or take a look at a video that the algorithm recommends to you.